Coulomb's law, electric field, and electric potential difference, some basic things you need to know. First, Coulomb's law is this equation, shows the force between any two charges that are a distance r apart. It's the center to center distance, it's not the radius. The Q's are the two charges in coulombs, and the K is Coulomb's constant, the electrostatic constant, 9 times 10 to the 9 Newton meter squared per Coulomb squared. See this F subscript E or subscript Q depending on the book, that force, it's a force in newtons, just like every other force. Electric field, that's this one, electric field is actually altered space. If you have a charge, space is altered. There doesn't have to be any mass there, but space is altered. Altered space around a charge where forces would be applied to charges if they were placed there or when they are placed there. And the equation, E equals F over Q, force, this is the electric field strength. The electric field strength is the force per Coulomb, where forces would be applied, force per Coulomb at a particular point in space. And it is a value for the point in space. It's about the altered space, force per Coulomb. And this KQ over R squared is the equation that you could use for a point charge. This is not a complicated equation. This is not something totally different. This is just a combination of those two. If you take the electric field strength, which is force over charge at a particular point in space, all you're doing is taking this equation up here and dropping a Q out of it. You get KQ over R squared. By taking this, dividing by one charge, you get E is equal to KQ over R squared. Work and electric potential energy and kinetic energy, QED. Gravitational potential energy is mgh. M, mass in kilograms, important in gravitational force. Q, important in electrostatic force and charges. The gravitational field strength, that's what the G is. The electric field strength, that's what that E is. This is the height, the distance parallel to the field. And this is also the distance parallel to the field. So work, electric potential energy, work, gravitational potential energy, kinetic energy, work, electric potential energy, kinetic energy can all be found using QED or QV. Now this V thing, that electric potential difference, or the voltage, is something we specifically use for this, for electrostatics and electricity, but it also exists here. It is GH. The gravitational potential difference is GH, and it is in the field, the gravitational field strength multiplied by the vertical distance, the parallel distance between the 2 points that you're talking about. And the definition, which is important, voltage is electric potential difference. So if you hear or read electric potential difference, translate that into voltage immediately. When you hear voltage, translate that into electric potential difference. It's related to the equation I have over here, but here's the definition. It is the energy difference, or the work done, or the potential energy difference, or the kinetic energy difference per Coulomb between 2 points. So we just took this QED, that electric potential energy of the work divided by charge, got rid of the Q, ended up with ED. So it's V is work done divided by the charge. It's work done parallel to the field. Electric potential energy divided by the charge. So QED divided by the charge, which is ED. And you have the voltage is the electric field strength times the distance between those 2 points. And remember, one thing you have to remember throughout this entire thing is that our preferred charge, not just because of Benjamin Franklin, because he liked positive, but our preferred charge is positive. Everybody does positive is what we prefer. We use positive constantly. That's just what we do. So remember, the preferred charge is positive. The higher potential is positive. The electric field is drawn using small imaginary positive test charges. Why? Just because. You pick one, you be consistent. We picked positive, and we're going to be consistent with that. Can you read this? If you can't read it because you're all squinty, then there's an entire front row that's totally empty. Move up so you can read the thing. It's not that hard. Or pull out your opera glasses. Here's a plate, left-hand side, positively charged plate here, negatively charged plate here. First sketch the electric field between those 2 plates. What's the direction? Point to the direction of the electric field. Should these lines be all parallel to each other?
Yes.
Yeah, and they should be all like evenly spaced, right? So like that, and like that, and that, that. What about the edges? So they do this. So at the edges, this is a uniform field except at the edges. And remember, these are parallel plates. So this is a plate, and it's a plate. This is 3 dimensions. We're attempting to demonstrate this on a 2-dimensional system. Now, a proton placed in this field, this is the first question. This is a question up at the top, and we've done some of these already. A proton placed in that field will accelerate to the point. Are you pointing? You're pointing, right? So, pointing right. Okay, so to the right. Because again, by definition, this electric field is defined, because we prefer positive, as the net force direction on a positive test charge placed there. And question number 2. What's that say, Justin?
When the electron placed in this field will tend to accelerate to the left.
To the left. Net force applied to a positive charge in this field is directed to the, let's see, net force, but positive charge is the same as a proton, right? So if it says proton, if it says positive charge, it's going to be the exact same answer. And then the net force applied to a negative, it's a negative charge. So the general rule, the force applied to a positive charge will be with the field, and the force applied to a negative charge will be against the field. Now, find the net force on a 5 microcoulomb charge. Put a little thing right here, positive 5 microcoulomb charge in the field above. Did you find it yet? Well, it was homework, so you should have. What equation, Olivia, did you use?
The electric field equals force over the charge.
Equals F over Q. These are vector equations, electric field and force. Just find the force is equal to the charge times the electric field strength, and you get what?
25 times 10 to the negative 5 newtons to the right.
Or 2.5 times 10 to the negative
No, yeah, it's 2.5. And had
4.
Yeah.
4, and the units are what? 4 newtons. So the force is 2.5 times 10 to the negative 4 newtons, and that is a positive charge, so it would be to the right. And find the net force on a negative 10 microcoulomb charge placed in that exact same field. So you put that thing in there, negative 10 microcoulombs. Put that in there, you know the direction is going to be left. Do the exact same thing, and you get what?
5 times 10 to the negative 4th newtons going left.
Got those? Now you know already that when you lift something, grab something and lift it, in the gravitational field you're doing work. You lower it, you're doing work. Now what about this direction? No work in that direction. All right, so let me erase this garbage here. Doesn't help if you put the charge in there on the piece of paper and then imagine doing it. It does. So you may want to just imagine that you have a charge in your hand, you imagine this thing actually happening. And just as before, there are plates, and just as before, you have positive and negative plates. And this just shows the uniform field region. So for number 7, what kind of work is done to move a proton to the left? So to the left, you're going to take a proton and move it in this direction. What kind of work are you doing to move it to the left?
positive.
Positive. We have a positive. You agree with positive? Take a proton. Wait a minute. You're taking a proton, moving it to the left. Doesn't it naturally go that way? Doesn't something naturally fall, and aren't you lowering it? You take a positive charge, you put it in that field. If you are moving it, what's the direction of the force you have to apply? You are moving it, right? Same thing as a gravitational field. If you grab this thing and you move it in that direction, you have to keep it from, if you let go, what's going to happen to it? It's going to zip in this direction, right? So you have to hold it in that direction. The force applied is in that direction. The displacement is in that direction. And so, negative work. Move a positive charge perpendicular to the field. So in this case, I'm going to take the positive charge. Just going to take it and move it in this direction. Just that way or that way. Claire?
Why was the force negative though? Because wouldn't it be drawn to the left?
Yeah, and what do you have to do? You're taking that thing, right? You are moving it. If you let it go, then work would be done by the gravitational force. Work would be done by the field. But
Are you moving it?
you are moving it, yes. You are moving it. It's not, it's falling all by itself. You are moving it. And since you are moving it, you have to imagine that you're grabbing this thing, grabbing that charge, and you're moving it in this direction. Just the exact same thing we just went over. When you're grabbing something, you lift it up as you are moving it against the field. Force up, displacement up, that is positive work done. But as you are lowering it, It's like you're taking this positive charge and you're resisting its acceleration as you're lowering it in the field. And you have to do negative work to it. So this is you doing the work. And you take this thing, and you take that work done, positive charge perpendicular to the field, so you're going to move it in that direction. It does help if you draw stuff on here. What's the direction of the force you have to apply to cause that to happen?
There is none.
Oh, there is. Just like this. What's the direction of force you have to apply in the gravitational field? You are grabbing this thing, right? Exactly. You're grabbing this thing, and as you move it in this direction, what force do you have to apply to it to slowly move it in that direction? A force. If you release it, where's it going to go? What do you have to do to keep it from doing that? Slowly move it in this direction. How much work is done?
0.
None. Now you take this thing, take that same exact positive charge, put it in there again. I'm going to move it, let's see what kind of work is done if a positive charge is moved to the right. Okay, I'm going to take this positive charge, I'm going to move it to the right. So that will be the displacement. What force direction is there? I'm going to push it to get it there, right? So if I'm going to push it to get it there, oh, the force and the displacement are in the same direction. And so this would be positive work. You are moving this thing. You grab it, you move it. And now, how much work would be done by you if you moved a 3 millicoulomb charge 10 centimeters perpendicular to the field toward the top of the page? Treat all these things as individuals if you want, or refer to the ones up above. And this is a 3 millicoulomb charge. I want to move it in this direction. How much work would be done? Answer is? 0. There isn't any. Because the force necessary to keep it from accelerating toward the negative plate is to the right. How much work would be done by you if you moved a 10 millicoulomb charge 20 centimeters, 10 millicoulombs, 10 millicoulombs positive, and that is in the same direction as the field. So displacement is in this direction. You're grabbing it, you're moving it. What's the direction of the force you have to apply? So the force is in that direction to keep it from just flying out of your hand. And then the, labeled that already. And how do you find it? So the answer is going to be negative. What do you do? Use the equation for work, or the change in electric potential energy. Take the charge, multiply by the electric field strength, multiply by the distance. Do that calculation. Millicoulombs times 10 to the negative 3.005. Multiply by the electric field strength given. And if this field extended 20 centimeters, which in my problem it doesn't, but if it did, you just multiply that by 0.2 meters.
Why is it 5 times 10 to the negative 3?
Millicoulombs, right?
Yeah. But why is it 10? Are we on 11?
Well, it would be 10 times.
Should be 10 then, right? Should be 10 times 10 to the negative 3. Is that what you were saying?
Yeah.
Yeah, 10 times 10 to the negative 3. 0.1? 0.1? 0.1? Did you get, okay, so negative 0.1, negative 0.1, and the answer would be in what units? Work. Joules. You're going to go back and think about the things you've already done. Work is in joules. This new situation is 50 newtons per coulomb. Distance is 1 centimeter between those two plates. The electric field is to the left in this case. How much work would be done by you if you moved a negative 20 microcoulomb charge 1 centimeter in the same direction as the field? Work done, QED or QV, either one. You don't know the voltage at this point yet. We haven't done anything with that. So it's just Q times E times D. You take the negative 20 times 10 to the negative 6 times the electric field strength, which is 50 newtons per coulomb, times the distance of 0.01 meters, and you get the work done. How much? 0.0001 joules. Is that positive or negative? This is where you take the thing in your hand and imagine that you're doing it. You take a negative 20 microcoulomb charge in the same direction as the field. So you take this negative same direction as the field. Do you have to push it to get it there? You take a negative charge. Do you have to push it to get it toward the negative plate? Where's it going to go if you let it go? It's going to go that way, right? What do you have to do to get it? You have to push it. So if you push it, you're pushing it in the same direction as it's going. Is that positive or negative work? Everyone? Positive. So, positive. Did you get a negative number in there? Yeah, because you put the negative in there. And as I told you before, when I do problems like this, with this one, I don't put negatives in there because then I start, like in this problem, depending upon the sign for the answer. And it's a bad idea. Take a negative charge and I'm moving it in the same direction as the field. I have to push it to get it there. So I'm pushing in the same direction as it's moving. Positive work done. Whatever my calculation is without the negative in there, put a positive on. And then as a result of my pushing it, how much more potential energy will the above negative charge now have? How much more gravitational potential energy or electric potential energy does it have? It's the exact same number. You did these problems already. Remember back when we did the gravitational potential energy? Oh, I added 7 joules of, well, I did 7 joules of work to it. What does it now have? 7 joules of gravitational potential energy. I did 0.0001 joules of work to it. What does it now have? Oh, it now has the exact same amount of more potential energy. It's actually also in the equation. It's right here. See the work? W work done is equal to the, oh, it's right there. Or the change in kinetic energy.
And there should be one more.
There should be like one more zero than that? One more?
I got 1 times 10 to the negative.
1 times 10 to the negative fifth would be one additional zero.
Yeah.
You like 1 additional zero? Can you people give me the right numbers? What?
I have that.
You. Okay. Next question. Did you answer this one yet? Where would a proton have the most electric potential energy? Okay, where would a proton have the most electric potential energy?
Is that the left way?
Well, that,
Oh, the right way.
why?
Because you're like fighting against.
Because you're fighting against the field that already exists. Why? You take this thing, where does it have the most electric potential energy? You take it where when you release it, it would have the most kinetic. So you just push it over here, right plate. Where would an electron have the most electric potential energy? Why? That's where all the electrons are. You put a whole bunch of electrons together, what happens to that single electron that's free to move? You release it, zip, it zips in the opposite direction. So, negative. And the next question, positive charge must be released from where to gain the most kinetic energy? Right side, positive plate. And a negative charge must be released from where to gain the most kinetic energy? Sean? Negative plate.
Don't they need more potential energy and more thinking of work? Shouldn't it be reversed?
Work and potential energy and kinetic energy are all related to each other. I do positive work to this. And if I do positive work, it has more gravitational potential energy, correct? And that gravitational potential energy, when I release it, can turn into a whole bunch of kinetic energy, right? So, if I am lowering it in the field, I am doing negative work. So, force, displacement, negative work. And as I lower it, what happens to its gravitational potential energy? Decreases. And what happens to its maximum kinetic energy if released? Not as much. Higher you are, and this is all you're doing, this is exactly the same thing, except you're considering now, oh, it could be different based on the charge that I'm moving to different locations. And 2 questions are linked here. Where would a proton have the most electric potential energy? From the positive plate. A positive charge must be released. Those 2 are basically the same question. Where would it have the most electric potential energy? And where would you release it to get the most kinetic? Same thing. And where would this thing have, where would the electron have the most electric potential energy? And where can you release it to get the most kinetic? Same answer. Which charge do we prefer? Positive. Which plate has the higher potential? Positive. Just by definition, always, every single time. The more positive plate or the positive plate always, always, always has the higher potential. Which plate's at the higher potential for an electron?
The positive.
Why?
Physics.
Because we prefer the positive and the electron doesn't matter. That's why. It's always the same every time. And which plate's at the higher potential for a proton? Nope. Yep, why? Because it always is. It always is. By our definition, we like positive. And it always is. In what direction would an electron have to move for a positive potential difference? Nope. Why?
Because it's attracted to the.
Nope. Which one's the higher potential? Positive. You want a positive potential difference. You want to move toward the positive every time. It doesn't matter what charge you put in there. Toward the positive. So this answer right here, what up? Whatever. Doesn't matter what charge it is. You just like put a instead of that. Because which one is the higher potential? By definition, this thing over here is. It doesn't matter if I put a negative charge or a positive charge in the middle there. That doesn't matter one single bit. By our definition, our preference is left-hand plate, the positive plate, that's the higher potential. You want to get a positive potential difference, you want to move toward the higher potential. This, by definition, toward the positive. And let's translate this one again. Number 22, in what direction would a...
Doesn't matter.
Doesn't matter. In what direction would a whatever charge have to move for a negative potential difference? You're moving toward the which one? Negative. You're losing potential. You're going to a lower potential. This is toward the negative. And now 23, find the electric potential difference from the left plate to the right plate. When you hear electric potential difference, you immediately think what? Voltage. And what's the equation over here? V is equal to that over that, or that over that, or that over that, or that. Which one's easiest? ED. So V is equal to ED. Take the E, multiply by the D, and then determine whether it's positive or negative. 5/100 of 100 is what? 5. And that would be what units? The units for voltage are volts. Joules per Coulomb, and this shows it right here. Voltage, joules per Coulomb, because you know that work is joules and charge is coulombs. And electric potential energy is joules and charge is coulombs. And it's joules per Coulomb or volts. And if you're going from the left to the right, from left to right, is that a loss of potential or a gain? It's a loss, right? We just determined that in the ones up above. You're going to a lower potential, so it's a loss of potential. It's a negative 5 volts, negative 5 joules per Coulomb. Just by definition, because we prefer positive just because.
Wouldn't the 5 be 5/10 because you're making it into...
This is 0.05. 5/100 times 100 gives you 5. And then the electric potential difference from the right plate to the left plate. Answer is? Five. Positive or negative? Positive. You're moving toward the higher potential. Positive 5 volts. 24. Because at the edges, so in the middle, you have uniform electric field, and these plates are usually really small. If they're close together for the sides, so they should be the same size, but they're really close together for the surface area. At the edges, like out here, these things are parallel plates. At the edges, there's no charge out here to keep it from bowing out, so it bows out. Because any positive charge, these electric field lines represent the net force on a positive charge. And out here, you take a little tiny imaginary positive test charge, and the positive charge is going to repel it, and the negative charge is going to attract it. And over here, the positive charge is going to repel it, and the negative charge is going to attract it. And so you end up having a graph that looks like that. This represents the tangent line would be the net force applied to an imaginary positive test charge there, just at the edges. So this is uniform except at the edges of the plates on all four sides. Ready for the next one? This one is about electric potential difference and potential energy. And we're using these bottom two equations here. Electric potential difference between 2 points separated by 10 centimeters. If the distance between them is perpendicular to the field. Oh, you see that perpendicular? What does that mean? Say it. What does it mean? No work done. No change in potential energy. It's just dragging something along, or just carrying something along horizontally in our gravitational field. So it's between this point and that point. No work done, no electric potential difference. Watch for that term right there, or watch for 2 points perpendicular. You have to be parallel to the field to get a potential difference. Number 26, find the electric potential difference from one point in the field to another point, 2 centimeters to the left. So I'm going from here to here, 2 centimeters. Is that going to be a positive or a negative? Positive, how do you know? Because by definition, the positive one, this positive plate, is the higher. This is the lower. So if that's the higher and the lower, and you're moving toward the higher, what do you get? You get a positive difference. Electric potential difference is the field strength multiplied by the distance. What'd you get there? 1.6. You take the 2 centimeters, which is right here, multiply by the, it's 0.02 times 80 gives you 1.6 volts. Positive 1.6 volts. How much electric potential energy would a proton have at the left plate? What do you have to do? Pick the proper equation for electric potential energy, pick the proper form of it, the proper pieces, and put it together. Electric potential energy, and this is on your reference tables too, and that's what you should be looking at. This is a reproduction of that. Electric potential energy, QED. Can you do QED? Yeah, pretty easy. Charge, 1.6 times 10 to the negative 19. Multiplied by the electric field strength. And by the way, before you do the calculation, make sure that it does have electric potential energy. Will a proton, if sitting here when released, will it accelerate in that direction? So does it have electric potential energy? It does, so you can then do the calculation. Multiplied by the 80 newtons per Coulomb, multiplied by the 3 centimeters.
I got 3.84 times 10 to the negative 19.
Did you get that number? Yeah? Okay, so 3.84 times 10 to the negative 19. Proton above is released from the positive plate, so it's positive over here. Let it go. Where does it go? Zips in that direction, picks up speed, picks up kinetic energy, and how much kinetic energy does it have just before it strikes the right-hand plate? Yes, Claire? It's the exact same number, 3.84 times 10 to the negative 19. So we have a elastic or electric potential energy to kinetic energy conversion, and that is 3.84 times 10 to the negative 19 joules. Okay.
When you were saying that it would have potential energy on the...
If you take a proton, you grab a proton, you just grab a proton from right here, and you put it right there. You know that it has electric potential energy because when you release it, it will zip in that direction. However, if you take a positive charge or a proton, you put it here, what's it going to do? It doesn't have potential energy. It's the same thing as this thing. It sits on the floor. That's like on one plate. It's sitting on the floor. How much gravitational potential energy does it have in this room? If, however, you lift this and you put it on the ceiling, does that have gravitational potential energy in this room? Yeah, so that's the idea. You just put it in there in your brain. Imagine what it's going to do. And now we need to find the speed of a proton as it reaches the negative plate. So the proton starts out over here, is released, and speeds up. The electric potential energy turns into kinetic energy, and that kinetic energy we can use to find the velocity. Now, that's not an equation from this chapter. We go back to kinetic energy is 1/2 mv squared and solve for that v. Kinetic energy is 3.84 times 10 to the negative 19 joules. A half times the mass of the proton, 1.67 times 10 to the negative 27 kilograms. Solve that for 21,400 meters per second. Final speed of the proton, and if you're looking for the final velocity, it's 21,400 meters per second in that direction. When you release the proton from the positive plate, let it move. This is a group, and that's a group. Same direction of electric field from the positive plate to the negative plate. This is the higher potential, this is the lower potential. Again, by definition, the positive plate is the higher potential, negative plate is the lower potential. Move in this direction toward the lower potential, that is a loss of potential. A negative potential difference toward the positive, toward the higher potential, that is a positive potential difference. Number 30, how much electric potential energy would an electron have at the left plate? So electric potential energy is equal to QED. But before you do the calculation, think about the thing. How much electric potential energy would an electron have at the left plate? None. Because when you release it, where's it going to go? Nowhere. So this is 0. The electron above is released from the positive plate. Find its kinetic energy as it reaches the negative plate. Answer does not exist. It won't go anywhere. It won't reach the negative plate. And of course, this answer does not exist. So before you solve problems, make sure that the situation described is possible. Don't be wasting your time solving problems if the situation isn't possible. Numbers 33, 34, 35, how much electric potential energy would an electron have at the right plate? Oh, now that's a possibility. This is the negative plate. You release that thing, it's going to be repelled from the negative, attracted to the positive, pushed opposite the direction of the field. Now I can solve the problem, and that is 1.6 times 10 to the negative 19 coulombs multiplied by the electric field strength, 30 newtons per coulomb, multiplied by 7 centimeters. Remember, can't be in centimeters, has to be in meters. 0.07 meters. 3.36 times 10 to the negative 19 joules of electric potential energy. 34, the electron above is released from the negative plate, find its kinetic energy. Oh, well, that's just a conservation of energy thing. So this electric potential energy turns into kinetic energy. That's the exact same value, 3.36 times 10 to the negative 19 joules. Now find its velocity. Well, the velocity is going to be to the right. That's number 34. Number 35, kinetic energy, 1/2 mv squared. This is an electron. Kinetic energy, 3.36 times 10 to the negative 19 joules is equal to 1/2 times 9.11 times 10 to the negative 31 kilograms. From your reference tables, just a known value, v squared. 859,000 meters per second. That's the final velocity, and that would be in that direction. There you go, 859,000 meters per second for that final answer. Make sure that the situation is possible before you start solving the problem. And that is how you solve kinetic energy, electric potential energy, electric field strength, voltage, potential difference problems, and you can look at the things and really figure out a lot. First of all, determine if it's possible. Determine the direction of the force, the direction of the electric field strength, the direction of the acceleration, the direction of the velocity. You can look at it, determine whether it's an increase or a decrease in electric potential energy. You can determine whether or not it's an increase or a decrease in voltage, a positive or negative voltage, and solve the problems that way. So, good luck. You're going to need it.